organizers for inviting me here to tell you about some of the research that my group has been doing for the past few years at Columbia. So what I'm going to tell you about today is a story that a subject that my group has been focusing on, looking at the technologies focus on beyond lithium-ion batteries. And just to give you a little preface about why we care about beyond lithium systems. Some of the most obvious reasons to move beyond lithium-ion batteries is that things like sodium and potassium are about 1,000 times more abundant than lithium in the Earth's crust. But when we think about the active ion, that's not really the only thing that matters whenever you put it into a alkali metal battery. We also have to think about all the other components that are going inside. So we have to think about things like the current collector. We have to think about things like the cathode, which is usually some type of porous structure or transition metal oxide. And these have lots of different elements inside of them. And this turns out that whenever we move from lithium to sodium or potassium, that we're actually going to be using elements that are also much more abundant. So things like manganese or iron. And so these are actually going to make our batteries a lot more cheaper. But all of these elements are actually much more evenly distributed throughout the globe compared to lithium and a lot of the other elements that are currently used in a lithium battery. So things like nickel or cobalt. And this is going to give us greater energy democratization as we move beyond lithium-ion technologies. Then from a fundamental research perspective, as we move down the periodic table from lithium to sodium to potassium, in principle, we wouldn't think that very much about our chemistry is going to change, right? We still have these monovalent ions. Things should act pretty similar. All we're really doing is making our active ion larger. But what we found, and what I'll tell you about today, is that actually a lot of the things about our chemistry is going to change in unexpected ways. And this is really exciting from a research perspective because it gives us lots of opportunities to optimize this chemistry in ways that's really, really interesting. Okay, so just to orient everyone in the audience, this is what an alkali metal battery looks like whenever we look inside of it. So we have our alkali ions. These are highlighted in red. This is the anode side of the battery. So this is our negative terminal. This is our cathode side of the battery. This is our positive terminal. And then in the center here, we have a separator. This is soaked with our liquid electrolyte, and this is what allows our ions to be shuttled back and forth during charge and discharge of the battery. So this chemistry is highly reversible in a lithium-ion battery. And our goal whenever we move to sodium and potassium is to get that very high reversibility in these systems as well. Now, the question that we started to ask in my group whenever we looked at things like sodium and potassium ion batteries was, can we use the exact same battery materials, so our cathode, our anode, our electrolyte, in things like beyond lithium-ion chemistries? So what I'm going to tell you about for the most part today is potassium-ion batteries, and we're going to focus on the electrolyte, and I'll tell you why that is in just a minute. So a common electrolyte that you use in a lithium-ion battery is going to be a 1 molar salt of lithium PF6. And then you're going to have some carbonate-based solvents. So this is dimethyl carbonate, ethylene carbonate, and fluoroethylene carbonate. So we typically use a small amount of these fluorinated additives to improve the performance of our batteries. Now, if we take a look at the reason that we actually are using these salts and solvents here, we can just look at the electrochemical stability window that we have for these materials. So what I'm showing you on the top here is our operating voltage of our lithium battery, and this is where our carbonate electrolytes lie. So if we look at where our cathode materials are operating, it's somewhere around 4 volts here. So our carbonate solvents are very stable here, and we're not going to get a lot of breakdown at the positive electrode. All of our lithium ion batteries that we use in our cell phones and our electronics, in our electric vehicles, they're going to use a graphite anode. Our graphite anode is sitting below the electrochemical stability window of our carbonate solvents. So what happens whenever we start to use our lithium ion batteries is that our electrolyte is going to start to decompose. Those decomposition products are going to deposit on the surface of our graphite anode, and it's going to form something called our solid electrolyte interface. Those decomposition products are listed here. So we're typically going to form something like lithium fluoride, lithium carbonate, a variety of our anion breakdown products as well. So these phosphate-derived products. And then we're going to form a variety of organic breakdown products that are coming from our solvent as well. And then this forms a kinetically stabilized system that allows our battery to cycle for thousands of cycles like we're used to in order to have a functionally stable device that we can carry around in our pocket. So if we want to switch from something like lithium to potassium or even sodium, what we want to know is, okay, what kind of electrode material are we able to use, and how can we pair that with known electrolyte solvents and salts? What I'm showing you here in this graph on the left is how our sodium and potassium batteries are able to cycle with graphite in terms of the same intercalation reaction, just switching out that active ion. So this black line here shows what our voltage profile looks like for a lithium ion battery whenever it's paired with graphite. And this on the side here shows our end member product whenever we form lithium C6. So this is at the end of charge here. Whenever we form lithium C6, we get a volume expansion of about 10%. If we look at our sodium cell, what we'll see in this blue curve here is that we're actually not able to put any sodium ions into graphite. So a graphite anode is not going to work with a sodium ion battery. We actually have to use a completely different structure. What's interesting is that if we skip over sodium in the periodic table and we move to potassium, graphite starts to work again. And that's what we're showing here in this red line. Now, we don't actually put as many potassium ions into the graphite structure as we do in the case of lithium. That's because we have a larger atom that's actually going inside the structure. So instead of forming lithium C6, we form KC8. That's what I'm showing here on the right. So whenever we form KC8, we end up getting a 60% volume expansion. So our electrode material expands more than it does in the case of lithium. So in principle, whenever we're forming that solid electrolyte interface, we want to be able to form something that's more elastic to be able to accommodate that larger volume change that we get in our solid phase electrode. In lithium ion batteries, we've seen this problem before. So an alternative anode material that we have in lithium ion batteries is silicon. Silicon has a very, very large volume expansion of about 400%. And the way that we deal with this is that we have alternative electrolytes that can form more favorable solid electrolyte interface layers that are more elastic. So what we do in this case is we add in these electrolyte additives, so that fluoroethylene carbonate, and that can improve the capacity of our battery. So here I'm showing an electrolyte that does not contain any additives in black. So this is just our conventional carbonate electrolyte. We put in a little bit of that FEC additive and we get much better capacity retention. What happens whenever this fluoroethylene carbonate starts to decompose is we defluorinate the structure, we form some lithium fluoride, And then we also form this poly VC structure. This has been characterized with solid state NMR. And this is thought to be the elastic component of that SEI layer that can accommodate these very large volume expansions. Okay, so whenever my group first started to work on potassium ion batteries, we thought, okay, all we have to do in order to get very good performance when we have this 60% volume expansion is just to add a little bit of FEC to our electrolyte, and we would get much higher capacity retention whenever we started using these batteries. Okay, so this is what our electrochemical cycling data looks like. We're just using two different salts here. So this is our KPF6, this is our KFSI. These are just two different anions, and we have the same electrolyte solvent. This is starting the system with no fluoroethylene carbonate here. We get high capacity in our first cycle, and this is because we're cycling much more slowly. We speed up the cycling to speed up our experiment. And this is just the first few cycles that I'm showing you here. Next thing we do is we add FEC to the mixture, and we see something that is actually quite surprising. These green dots show that whenever we have FEC inside of our battery, instead of getting higher capacity and higher capacity retention, we actually end up killing our potassium ion batteries instead of improving their performance. So we have instant cell failure, and we actually get very high resistance in our batteries instead of getting lower resistance, which is what we would expect if we were improving the properties of that solid electrolyte interface layer. So what is actually going on to the chemistry that's deposited on the surface of our carbon electrode that we have in our potassium ion batteries? In order to answer this question, the first experiment that we do is run just a very simple solid state fluorine NMR, and we compare the results that we get whenever we do and do not have FEC in our electrolyte mixture. So what I'm showing you here in the bottom is the results from our battery whenever we just have KPF6 in our electrolyte versus those whenever we have added FEC to the mixture. So this peak here corresponds to our residual KPF6 that we have deposited on the surface of our battery. And then the asterisks here represent our spinning side bands. And the only other resonance that we have shows up in our sample whenever we have FEC in the battery. We don't actually have anything else whenever we just have KPF6 there. So whenever we have FEC, we get the sharp resonance that corresponds to our potassium fluoride. So this tells us that we actually aren't forming any potassium fluoride whenever we have KPF6 in our electrolyte. We also confirm this result by doing some X-ray photoelectron spectroscopy, where again, we only see that we form potassium fluoride in our solid electrolyte interface layer whenever we add FEC to our electrolyte. And what we noticed in this experiment is that the solid state NMR was crucial in order to getting this result. If we didn't perform this XPS experiment just right, we were actually able to induce some beam damage to these samples with the XPS and degrade this KPF6 salt. So we had to be very careful here and make sure we didn't induce the formation of KF whenever we had our KPF6 here. Okay, so in any case, what we noticed is that there was this strong correlation between the formation of potassium fluoride in our SEI and core performance in our potassium ion batteries. So what exactly was going on in these samples? So what we saw is that as we move from lithium fluoride to sodium fluoride to potassium fluoride, if we look in the literature in terms of both experimental values and what was being calculated with DFT, we expect that the ionic conductivity for these layers that we were depositing on the surface of our electrode we see that we get lower and lower ionic conductivity. So for lithium fluoride, the ionic conductivity is 10 to the minus 13 Siemens per centimeter. The predicted value for sodium fluoride is 10 to the minus 23 Siemens per centimeter, so a drop of 10 orders of magnitude. And then if we extrapolate down, we would expect this to be even lower for potassium fluoride. These lower values in terms of our ionic conductivity are expected for these binary salts. Whenever you have lower dielectric constants, you have less charge screening, and you're going to have this higher barrier to ionic diffusion through these layers in your SEI. Now, whenever you have these ionically blocking layers on the surface of your electrode, this correlates well with what we see in our electrochemistry. So as soon as we form this blocking layer on the surface of our electrode, we're not able to actually move our ions in and out of our carbon electrode. And this is why we can't actually extract any more capacity in. Okay. Now, by looking at these values that we see are reported for our metal fluorides, this led us to question, okay, so what is actually going on in the case of lithium fluoride in the first place? If we look at the values that people are trying to dial in for a good solid electrolyte, these are actually very, very different from what we see from lithium fluoride in the first place. So a good solid electrolyte, you want to get somewhere around 10 to the minus 3, 10 to the minus 4 Siemens per centimeter. But having lithium fluoride in the SEI is often reported to be a very, very good thing if you're trying to design a good electrolyte for a lithium battery, for example. So these two things don't necessarily mesh with one another. So what I'm showing you here on the right is data from the lithium metal battery literature, where you're looking at the advances in lithium electrolytes over the past several decades, where as you increase the fluorine content in your electrolyte, you see a dramatic increase in your Coulombic efficiency. As you increase the amount of fluorine in your electrolyte, you're increasing the amount of lithium fluoride that you are depositing on the surface of your electrode. Now, as you increase the amount of lithium fluoride in your electrode, in principle, you are just putting down a layer that is more and more ionically insulating. So if we have something that's ionically insulating, how is this correlated with high Coulombic efficiency in these lithium metal batteries? So this result that we see on the right led us to go back and re-examine, okay, what is it about the lithium fluoride that is in the SEI in these batteries that's actually enabling lithium metal to be deposited at very high current densities and achieve these very good performances in lithium metal batteries? In order to answer this question, we did an experiment where we examined the structure of the lithium fluoride that was deposited in the SEI on lithium metal anodes for a series of different electrolytes with a range of Coulombic efficiencies. So what you're looking at here in our fluorine solid state NMR is the lithium fluoride on our lithium metal electrodes from a low Coulombic efficiency electrolyte. So this is our conventional carbonate electrolyte versus electrolytes that give much higher Coulombic efficiencies. So this is a high concentration electrolyte, and this is a localized high concentration electrolyte. So this is really a state-of-the-art electrolyte that gives high Coulombic efficiency somewhere above 97%, whereas this is on the order of about 85%. And then this is somewhere in between, so somewhere around 95%. What we're doing on the bottom here is we're just comparing the line shape to bulk lithium fluoride. And then if we look at the changes in our line shape, we can see that as we increase the Coulombic efficiency, we see that we get the growth of this high frequency shoulder as we improve the Coulombic efficiency of our lithium metal battery. Now, what we think is happening to the lithium fluoride in the SEI here is that we're actually changing the structure of this material. So some of our lithium fluoride looks similar to our bulk lithium fluoride, and that's certainly the case whenever we have a low Coulombic efficiency electrolyte. But as we improve the Coulombic efficiency, we see this very broad peak that comes out. And we think that this is similar to something like amorphous lithium fluoride or lithium fluoride that contains a lot more grain boundaries with other components in our SEI. So our SEI is a composite that's made up of all different types of electrolyte decomposition products. Or this could be lithium fluoride that has a lot of different defects that actually improves the ion conduction of this material in our SEI. So just to put this in perspective a little bit more in terms of what we're seeing with our line shape. So our bulk lithium fluoride, it just gives us that single peak, and that's because we have one crystallographic site for our lithium fluoride there. And then, of course, if we have an amorphous structure, this would lead to all of our distinct chemical shifts that we see in that broader peak at the higher frequency there. And then again, this could be, very small lithium fluoride grains or defects that we have in fluoride. We're not exactly sure of the assignment in this resonance that we have here, but this is something that we're actively working on by making different types of model structures and model compounds and forming these SEIs in different ways and under different conditions in our batteries. Now, to understand how this is actually impacting the dynamics in our lithium fluoride phase of the SEI, similarly, we're also making different types of models in our lab. So a very straightforward way to be able to do this is to take bulk lithium fluoride and then just ball mill it. So this will reduce our particle size. This should also induce defects into the structure. And then we do see minor changes in our line shape here. So this is just an SEM image of the bulk lithium fluoride that we start off with in our lab. And then this is what the structures look like after 24 hours of ball milling. And then this is our solid state fluorine NMR. And you can see that we do indeed get this very small shoulder that pops out after ball milling. Whenever we look at our T1 measurements before and after ball milling, we do indeed see that we see changes in our fluorine dynamics. So we have very long T1s before ball milling of about 170 seconds. After ball milling, we see that these T1s get much, much shorter, and we have two components here. So about 20 seconds and about 7 seconds after ball milling, indicating that we do have changes in this structure that are consistent with changes in our dynamics, suggesting that potentially whenever we're changing the structure of our lithium fluoride, we are inducing changes in our dynamics that could change the ion conduction. Okay, so back to our story with our metal fluoride structures that we end up seeing in our potassium ion batteries. So just to reorient ourselves, whenever we did not have our fluoroethylene carbonate in our potassium ion batteries, we saw absolutely no KF. Whenever we added in our FEC, we ended up seeing our KF in our batteries. Now, one thing that was a little bit odd about this experiment was, again, how this deviated from what was known in lithium-ion batteries. So if we run this same exact experiment in a lithium-ion battery, and we have just our LiPF6 salt, we would always see the formation of lithium fluoride in our SEI. So this was very unusual that whenever we were cycling a battery with KPF6, that the salt was very resistant to reductive decomposition in the formation of KF, and that these batteries were actually able to cycle very well because they were not forming KF because of the lack of salt decomposition at all here. So what this caused us to do was to go back and revisit the mechanism of PF6 hydrolysis that was known from the lithium literature. So in the lithium literature, what happens is you have your LiPF6 salt. It's in equilibrium with this dissociation reaction where you form LiF and PF5. Once you form PF5, this can react with water, trace water in the electrolyte, forming POF3 and hydrofluoric acid. And then it undergoes several different decomposition steps to form a variety of organofluorophosphates and hydrofluoric acid. And we'll go in depth into these chemical reactions that form HF as one of the main decomposition products. Clearly, these reactions were not happening in the case of our PF6 salt whenever our potassium ions were there. In order to figure out what was happening in our potassium salts, we did a comparative analysis simply by adding water to our conventional carbonate solvents whenever we had lithium, sodium, and potassium as our countercations with our PF6. So in this experiment, we just take our 1 molar salts in ethylene carbonate and propylene carbonate, a 1-to-1 mixture, and we add 1.5 volume% water. And then we monitor these with fluorine and phosphorus NMR over the course of about a month. So this is just showing all 3 salts, and we don't necessarily have to go ahead and assign all these spectra yet. All we have to pay attention to for the purposes of this experiment is this region here that corresponds to our HF reaction byproduct. From a simple analysis here, you can just qualitatively assess that our lithium salt forms the most HF, our sodium salt forms a medium amount, and then our potassium salt is forming absolutely no hydrofluoric acid after the course of about a month. So this again tells us that our PF6 salt is not only stable against reductive decomposition, but is also very, very stable against hydrolytic decomposition. So we took this electrolyte and we continued to monitor it over the course of about 4 months. So this salt has actually been sitting in our lab for about 8 months now. I think we've continued to monitor it. We still don't see any decomposition. I'm highlighting this region here where we would expect to see our hydrofluoric acid. We see absolutely no trace hydrofluoric acid after 4 months. We've also taken these salts and we've heated them to 60 degrees C, compared them to their lithium counterparts. We see absolutely no decomposition in our fluorine or our phosphorus NMR, as shown in the red spectrum here. Whenever we compare to our lithium salts, we see all the expected hydrolytic decomposition products. These green spectra are very similar to what has been reported in the literature for the high temperature decomposition of LiPF6. So this is very well known. But again, we see no decomposition at high temperature for the PF6, indicating that the activation energy for this decomposition is higher. Okay, so whenever we take a look and we compare the decomposition of LiPF6 to NaPF6 to KPF6, we notice that this is likely a periodic trend that we're seeing here. And we think that it depends on the Lewis acidity of the countercation that's paired with our PF6. So what we think is happening here is if we look at this equilibrium that we have, We have our non-dissociated salt, and if we are pairing it with the proper solvent, we're actually able to push the equilibrium to this dissociated form. And whenever we're in this dissociated form, we are not going to form our metal fluoride and our PF5. We're going to be pushed all the way to the left. However, if we are in a solvent system where at least a portion is in the non-dissociated form, and we have an especially small countercation, so something like lithium, a strong Lewis acid, it can approach our fluorine, it can polarize this phosphorus fluorine bond, and then we are more likely to form our lithium fluoride, our PF5, and then from there, our hydrolysis reaction can proceed where we will form a plethora of our decomposition products. So because we did this analysis with NMR, we can take an in-depth look at exactly what is forming here and start to do some more in-depth structural assignments. So what we did in this experiment was we compared our phosphorus NMR using proton decoupling and not using proton decoupling. And we see a variety of new decomposition products that were not reported in the literature before. So we see these fluorine-containing products. So these were known from the literature, and these are known hydrolytic decomposition products. We see a variety of organophosphates and organofluorophosphates that are showing up here. But then we also see a variety of phosphonates that show up at much higher frequency in our phosphorus NMR. And we think that these might be important because these are structurally similar to some enzyme inhibitors that are known. So some of these are very innocuous, but some of these are similar to enzyme inhibitors that are much more toxic. So we want to keep in mind that these can form under certain water-containing conditions. And if we're looking at these in terms of recycling conditions, that we want to be very careful about whether or not these are going to leach into the environment and pose a threat to either human health or aquatic health whenever we're handling these in different manufacturing or recycling facilities. Well, you can also take a look. So all of these experiments that I showed you previously were performed at 1.5 volume% water. So these are at about 10,000 ppm. So these are much higher than would be encountered in a typical battery scenario. So we also want to be able to understand what would happen in the conditions where water would be produced during normal battery cycling. So we also took a look at, okay, what is the product distribution and the product quantity whenever we add something like 200 ppm. So this is similar to the water that would be evolved under high voltage battery cycling. And we do indeed see that we get a different product distribution and different product quantity, but the same products are eventually formed under similar timescales. So we see that we're forming the same organofluorophosphates, phosphonates, and organophosphates that we saw under the higher water conditions. Okay, so I mentioned earlier that our PF6 decomposition seems to trend with the Lewis acidity of our countercation. So the next question that we wanted to ask ourselves was, what happens if we add something like a proton to these electrolyte solutions? Would we expect to accelerate our PF6 decomposition even more? And are things like our sodium and our potassium electrolytes, no longer immune to our hydrolytic decomposition. So we had actually done some experiments that were a little bit similar to this in our lithium-ion batteries previously. So whenever you charge a lithium-ion battery, you end up forming protons simply by solvent oxidation. So this is an experiment that we did whenever we were paired with a spinel type cathode in a lithium-ion battery. So this is an operando experiment where we were monitoring HF formation with fluorine NMR and manganese dissolution due to acid etching with operando EPR. This is our voltage curve, and then we have select points where we're pulling out fluorine NMR and EPR spectra here. And you can see the spectra that correspond to HF, manganese, and then our different decomposition products from our PF6. On the right here just shows a summary of our reactions that are occurring during battery electrolyte and salt decomposition, as well as our cathode decomposition in this reaction. So it's pretty complex, but just to break this down in terms of what's happening here, we do see accelerated decomposition of our PF6 due to the formation of protons. And what's happening here is that our ethylene carbonate undergoes a dehydrogenation reaction due to oxidation here. So our ethylene carbonate loses 2 protons and we form vinylene carbonate. Once we form those protons can attack our PF6, forming PF5 and hydrofluoric acid. This solvent oxidation reaction is going to reduce our transition metals on our cathode surface, forming manganese 3+. This can be etched by our hydrofluoric acid that's in our electrolyte, leading to our dissolved manganese 2+. This is what's showing up in our EPR here. And this was a nice experiment that we were able to monitor all with operando magnetic resonance methods in this paper shown at the bottom here. So if this was being speeded up, even in the case of lithium, we did have reason to believe that the external addition of would also accelerate this in our sodium and our, potassium system as well. So in order to test this, what we did was we took those same sodium and potassium electrolytes, so just our 1 molar salts with, but instead of adding water, what we did in this experiment was we added 1.5 volume percent hydrochloric acid, and we saw very, very rapid decomposition of our PF6 salt. So previously what we did was we were monitoring these reactions over the course of a month. What you'll notice is that the time scale shown on the bottom here is now on the order of minutes. This reaction starts before we can even get our tubes into the NMR. And we see the growth and the concentration of our hydrofluoric acid is shown in these yellow dots here. So this is our data for our sodium electrolyte. This is our data for our potassium electrolyte. And you can see that the concentration grows quite rapidly in both cases after the addition of the hydrochloric acid. So no matter what, no matter how stable these anions are, whenever they are paired with our beyond lithium salts, as soon as we add those protons, they're going to start decomposing. So takeaway here is that if we have a sodium or a potassium system that has a cathode where that's going to oxidize our solvent and produce protons, we are indeed going to get very rapid decomposition of our electrolyte salt, even in our sodium or potassium system, where we are forming that hydrofluoric acid. Hydrofluoric acid is going to cause this cascade of electrolyte decomposition reactions that can impact our battery safety. It's going to cause degradation in terms of things like our transition metal etching. And this is going to impact how we design our interfaces in our beyond lithium ion batteries. Because these salts are more stable, we can potentially tune how we design those cathodes or our electrolytes so that we don't form protons in these systems, and maybe operate our batteries differently in beyond lithium ion systems, so that we avoid these reactions altogether, and perhaps design different approaches that maybe weren't possible in lithium systems where we are more prone to hydrolysis. And then just something else to consider is that when you don't have a real cathode in there, you're maybe going to form a different interfacial layer than you would whenever you have a complete battery. So this can also alter things that you're going to see in your experiments than you would in a system. Okay, so I'll finish there, and I'll finish just by thanking my students and my postdocs who did all of this work and did all of these experiments. Their names are bolded on the right here. I'll thank the funding agencies that actually supported this work. Thank you for your attention, and I am happy to answer any questions that you may have.
Thank you, Lauren, for this fantastic talk. It was very informative and engaging, and I'm sure the audience has learned a lot. So again, for the audience, if you have any questions, just type in the Q&A box, and I'd be happy to read them. I'll straight away take questions from the audience. So Evan Wenbo Zhao says, "Hi, Lauren, good to see you. Do you have a sense of the detection limit of fluorine NMR in terms of the thickness of the ACI on lithium metal?"
That's a really great question. We have been able to put very, very small amounts of lithium metal into a 1.9 millimeter rotor. I would say, let me think back. 1 milligram, maybe even less, and then our SEI is a fraction of that. Acquisition times, I would think, we've had to run for a day or two in order to get signal, but we've been pleasantly surprised with the amount of how little sample we need in order to get signal from our lithium fluoride in these samples. And like for the localized high concentration electrolytes, in the literature, they are about 5 nanometers or so. And another thing to mention for these samples, they are the lithium metal is very metallic, and it's very flat, and it doesn't contain very much SEI at all. So we are diluting these quite a bit in an inert matrix. So it's a very small amount of sample that we have in there. So
yeah, okay. I'm sure that answers Evan's question. Next, we'll move on to Professor Aaron Rossini's question. So he says, have you tried fluorine and lithium 2D head core experiments or reader type of experiments to confirm the assignment of your fluorine NMR spectra to amorphous lithium fluoride? And also it has a second part. Would it also be of interest to try similar proton and fluorine NMR experiments to see if other components of the electrolyte may be integrated with the amorphous lithium fluoride?
Yeah, I believe we've done the lithium fluorine heteronuclear correlation. We have not done a reader type experiment, but we are working on similar type experiments right now. Those are not completed yet. We have done proton fluorine experiments to see if protons had any role in the conduction there. Those types of compounds are not present in the high performance electrolytes that I discussed. And we do see those in other types of systems. Those show up at a different position in the fluorine NMR. So those show up at minus 152 ppm. And those are these are like those bifluoride type compounds. So we don't think that those are playing a role. But when they do show up, they are very low intensity. So I think we can interrogate those more in depth still for certain types of electrolytes.
Yeah, great. Okay, so next we'll take a question from Leo Gordon. So says, hey, Lauren, excellent talk as always. And I was very interested to see the different shift for the HF from the acid decomposition of KPF6, and also that there was no signal from the etching of the glass around minus 155 ppm, as was seen in others. Do you have any explanation for this?
And so none of these experiments that I was showing with the PF6 salt are run in glass. These are all run in FEP liners to avoid that. Was there a first part of the question too that I didn't?
So it's just they were interested to see different shift from the HF, from the acid decomposition of KPF6, and also there was no signal from the etching of the glass around minus 155 ppm, as it was seen for others. So any explanation for this?
So we think that this is due to differences in solvation environment whenever we see this difference in the shift. And in that paper, we have 2 experiments in our supporting information where we add hydrofluoric acid to different solvents. And we see the shift change from around minus 190 ppm to about minus 160-ish ppm.
Okay. Right. So then Aaron Rossini has a follow-up question to the previous discussion. So is there really amorphous lithium fluoride, or are susceptibility effects causing a shift? And the 2D NMR spectra could help to remove susceptibility broadening. So
that's a good question. I don't know off the top of my head. I don't know is the short answer. We would have to check. Yeah. Yeah.
Okay. Maybe I'll take a question from Nikita. So in the 1-month heating samples, we see broad features in the fluorine spectra. What could be the reason behind that? Do you have any idea? Any comments?
Oh, this is baseline, ruling baseline.
All right.
And this can be removed. We didn't remove this for this one, but we removed it, but we removed the baseline for the other ones.
Okay. Okay. All right. Next, I'll take question from Shravan Uppala. So says, great talk. I learned a lot. Could you please let me know if you observed similar battery cycling behavior of potassium fluoride ACI formation when you varied the electrolyte from FEC to any other fluorinated electrolytes, like linear fluorinated esters or carbonates?
We haven't looked at any of the fluorinated esters or other carbonates. My guess would be anything that is going to form a potassium fluoride, although the fluorinated ethers, I don't think will form this. They should be reductively stable, will be fine. But if you're going to form something that is potassium fluoride, that battery will cease to work unless you can form something that has like a very small particle size or is not going to be high in concentration of those species.
Okay, and also there was a second part of the question. Do you think adding additives can improve the performance of potassium-based batteries? Okay.
Yes, yeah, for sure. And I think it's going to depend on what that additive is. So we did a few experiments looking at like a triethyl phosphate additive, and that seemed helpful. We did some experiments looking at vinylene carbonate, that also seemed helpful. So as long as something is not going to decompose into an inorganic bulk ion insulator, it should be okay.
Right. Next, I'll take a question from Yuval Steinberg. They say, did you do any potassium NMR on any of your systems?
Yeah, so we actually have a potassium probe. We've done some salts. We tried to make KC8 and look at it. Making enough KC8 to get good potassium signal is a challenge in itself. So we weren't, that was a thing that we tried and we ended up abandoning just due to getting enough material. But it's something we're always thinking about. But we have a lot of potassium NMR of model compounds. So yeah.
Okay. Then the next question from Arafat Khan says, hi, Lauren. Thanks for the nice lecture. Did you run the operando NMR for fluorine? And if so, what kind of probe head is it?
We ran the operando NMR for the solution fluorine experiments, where we were looking at the lithium battery during cycling. That is just a standard solution probe, where we're putting in a 5mm NMR tube with a polymer liner, and we have 2 electrodes sitting inside of it. But yeah, just a standard solution probe.
Okay. And then I'll take this question from Nikita again. So in one of your slides, you show there's a formation of HF. So how is the formation of the HF was handled in the NMR experiments?
Yes, we work closely with EH&S. But yeah, so, and we also have the safety kit in our lab. So we make sure that we're following all protocols. All of our samples are also sealed in airtight J-Young tubes to make sure that everything is safe, sealed. And then whenever we're ready to disassemble, we always have to, well, we have the NMR data, so we're able to calculate the concentration, and then we can give that information to EH&S as well whenever we're disassembling and putting into our base models.
Yeah, great. So if there is any further question from the audience, please feel free to type that in the chat box. But yeah. And Shravan Upala says thank you and appreciate your explanation in his one of their previous questions. And so there's one question from Pascal Schlochen probe. So hi Lauren, great talk. If I remember correctly, the SEI is usually thinner if FEC is added to the electrolyte. Is there a known relationship between the thickness of an SEI and the ion conductivity of the SEI components?
Yeah, I think it's going to depend on whether or not that SEI, that electrode is continuously cracking and then having to reform. We didn't do any direct measurements in the potassium battery of the thickness of the SEI. Based on how high the resistance got, it didn't give any evidence that it was thinner. It would actually point to the fact that it was thicker. I don't know if that's because it was less stable, maybe it was cracking and then reforming. But if it were thinner, then in principle, it could be that it had better ion conduction.
Yeah, thank you. So we have another question. Very nice talk. Why the NMR signals of the amorphous lithium fluoride formed by ball milling is much sharper than the real SEI?
Yeah, I think it's because ball milling is not the best
Yeah.
way to go about this experiment. Yeah, and when we took a closer look at our SEM, we still had a very large amount of micron-sized particles after ball milling even. And it was very difficult to downsize. What we were hoping was to go from micron-sized particles to nanometer-sized particles, because what we have in our SEI, or at least get close to nanometer size, what we have in our SEI, you know, at most is probably a 5 nanometer particle. And that's just not something that we can obtain with ball milling. And so we think that, yeah, that's why we still have these very sharp peaks that look bulk-like. The population that is small is just a very small fraction of our sample.
Okay. Excellent. So we're almost near to our session, and there's another question from Aaron. So what about some sort of solution phase colloidal synthesis for lithium fluoride?
I would love that. I have asked so many people to make me solution phase lithium fluoride nanoparticles, or any type of like deposition method to make nano-sized lithium fluoride particles. Everyone has told me no. If you know someone who can do this, I am all ears. But yeah, my guess is that they grow much larger than that. And this is why lithium fluoride is such a thermodynamic sink. And then once you form it, it just ends up getting much, much larger as soon as it forms. And then I also think that once it forms, it's so stable, you don't have a lot of defects, and it's very crystalline too once it forms. And so I have been searching everywhere to get someone to make me a model lithium fluoride that is, nanoparticulate, and I will take any nano size. It doesn't have to be the 5. But yeah.